In this video, through a solved example, we will try and understand why a bank needs to have in place equity capital as a buffer against credit risk related losses, and we'll also take a look at how to estimate the equity capital required, both from a regulatory perspective, a capital number which is referred to as regulatory capital, and also from an internal perspective, a capital number which is referred to as economic capital. Okay, so we are given that there is a bank ABC which has a very well diversified portfolio of loans. The aggregate loan size is given to us. It's $840 million. And because this loan portfolio is a very well diversified portfolio, we can assume that the granularity of this portfolio is actually quite high. High granularity essentially means that the number of borrowers to whom this entire sum of money of 840 million has been lent to is actually quite high. Let's denote the number of borrowers to be lowercase n, and a well-diversified portfolio means that this lowercase n is actually very high. Okay, let's begin by assuming that the horizon that we have chosen is 1 year, and let's write down the formula to determine the total credit risk related loss incurred or realized on this portfolio over the upcoming period of 1 year. Okay, for this purpose, let me assume that to each of these n borrowers I have lent a sum of money which is lowercase v. Okay, I am focusing only on the principal part. I am not focusing on the interest part as far as my calculations are concerned. Okay, so if I have lent out this much amount of money to each of my n borrowers, and let's say if any one of these n were to default, how much do I stand to lose? Let's assume that if a borrower defaults, I don't really lose the entire principal. I am able to recover some portion of it. Let that portion which is recovered be denoted by the recovery rate R. Please note that R is expressed on a per dollar basis. Okay, so therefore 1 minus R, which is referred to as the loss rate, is also on a per dollar basis. Okay, so if one borrower defaults, the total loss which bank ABC incurs is V times 1 minus R. If these many borrowers default over the upcoming period of 1 year, the total loss L will be V times 1 minus R times the number of borrowers defaulting. Okay, so if I am standing as of today, this number is not really known to me, and therefore I have denoted it by a capital letter in the spirit of denoting random variables by an uppercase letter. Okay, so in practice, please note that there are 3 terms which I have written here to calculate my loss, and in practice all these 3 terms have some amount of variability attached to them. Okay, so these 3 terms respectively, which are known as exposure, loss given default, and default, right? These 3 terms can be thought of to be 3 different sources of risk: exposure risk, recovery risk, or let's say loss given default risk, and default risk. Okay, so in this particular very simple question, actually what we'll do is that we will assume that these 2 guys can be assumed to be known with certainty, and it's only this guy which is our source of risk. Okay, let's do this. Let's divide this guy by the total number of borrowers and multiply this guy by the number of borrowers. Okay, so n times V I know is 840 million, the total amount which has been lent out. N sub D divided by N, let's replace it with a new random variable X. where X denotes the default rate. Okay, the number of borrowers defaulted, that divided by total number of borrowers. In the question, it's given to us that historically speaking, an average recovery rate is 45%, and therefore substituting the value of R and simplifying this expression tells me that the total loss is actually 462 times X $1,000,000. Okay, the next step would be to arrive at a distribution of the losses, and the way we have expressed our losses, the distribution of losses would depend on the chosen distribution for X, our default rate. Okay, now if I were to go and take a look at how X is defined, it's defined as n sub d, the number of defaults, that divided by n. Since n sub d is a discrete random variable, it tells me that X is also a discrete random variable. But since I am assuming that it's a well-diversified portfolio and hence n is quite high, it's not a bad approximation to assume that X is actually very close to being a continuous random variable. Okay, so we can search for an appropriate distribution for X picked from the continuous world. Okay, now another thing to note about X is that it's a variable which in some sense decides the severity of the loss. Also, it's a variable which is bounded in some sense, right? X, if you note carefully, can only take values between 0 and 1. And that's because n sub d can only take values between 0 and n, right? Since X is bounded from below by this number 0, X is always greater than or equal to 0. I mean, a good choice of distribution of X is actually the log normal distribution. Shape-wise also, if X is log normally distributed, which means L is log normally distributed, the shape of the distribution of L, which would look something like this, would be kind of matching what we generally empirically observe as the distribution of credit losses. Distribution of credit losses do have some amount of asymmetry attached to them, and the log normal distribution does provide that asymmetry. Okay, so let's choose the log normal distribution for X and therefore the log normal distribution for L. In the question, it's given to us that the natural log of X has a mean of minus 4.589 and standard deviation of 0.88, so variance of 0.88 squared. Since I am assuming that X is log normally distributed, it means that the natural log of X is normally distributed with this as the mean and this as the variance. Recall the properties of the log normal distribution and very quickly write down what should the expected value of X be. It will very simply be equal to e to the power this guy, the mean of the log of X, plus the variance of the log of X divided by 2. Okay, plug in these values into your calculator and please confirm that the expected value of X comes out to 1.497%. Okay, this is as far as the distribution, I mean the expected value of X is concerned. Plug this value into this formula for the L and find out what is the expected loss. It will be 462 times 1.497%, and that is 6.915 million. Okay, so I have plotted the loss distribution here and I have marked the expected loss of 6.915 million. Okay, now this is about the distribution of my credit loss. Now let's discuss very quickly the capital, the equity capital that this portfolio will require. Okay, so if I were to assume that the defaults of my n borrowers are in fact independent of each other, right, then I can prove this actually very simply, that this assumption actually points to this conclusion. And the conclusion is that if defaults are independent, the default rate X will actually be very, very close to the probability of default of each individual borrower. I'm assuming my loan portfolio is quite homogeneous, and hence the default probability of each of the n borrowers is actually the same. Okay, how does this conclusion come about? Without doing the mathematical proof, actually you can think about this, or you can rationalize this conclusion by simply invoking, let's say, the law of large numbers. Because I am talking about a very well diversified portfolio, it means that it's like I am conducting an experiment many times. Okay, each borrower in my portfolio can be thought of as an individual trial of an experiment. So if I were to repeat an experiment many times, for example, let's say if I were to toss a coin many times, then the observed incidence of heads, that divided by the total number of trials, should be very close to 0.5, which is the theoretical probability of obtaining heads. The same thing applies here also. If I have a very well diversified portfolio, that means I have many trials of the experiment, then the incidence of default, let's say as captured by this default rate, should be very close to the theoretical or assumed probability of default, right? So if X is very close to the assumed probability of default of each individual borrower, it means that X does not have too much of variation attached to it. It's actually very close to its expected value, which is the assumed probability of default. If X doesn't have too much of variation attached to it, it means that 462 times X, which is my loss, also will not have too much of variation attached to it. Loss will be actually very close to the expected loss. Okay, this from a credit risk management standpoint is a very simple situation to deal with. All you have to do is you have to start charging your borrowers a little bit extra, let's say as a spread on top of the interest rate that you charge to your borrowers, and you have to charge enough so that from all your n borrowers you are able to extract a sum of money which equals this amount. I mean the total expected loss. If I were to place this amount of money which I have charged to my borrowers into a provision account, I'm actually done. When these losses actually happen, and I'm saying that in this particular case there is a high amount of predictability associated with these losses, I have a provision account in place that I can use as a buffer against these losses. Okay, please note that expected losses are a part and parcel of a lending business, and you need to charge your customers enough for you to be able to fill your provision account as a buffer, to be a buffer against these expected losses. Okay, now this is an assumption which is difficult to defend in practice, this assumption of independent defaults. If you were to take a look at the behavior of your borrowers, what you will observe if you were to go one layer deeper is that your borrowers are affected by, or let's say are influenced by, a number of common factors. Okay, so these common factors are factors such as, let's say, factors related to the overall economy. When the overall economy is good, your default rate will be low. When the overall economy is bad, your default rate will be high. Okay, so if this assumption was telling you that default rate from one year to the next does not vary that much, relaxing this assumption and assuming that there are common factors which govern your borrowers tells me that your default rate will be variable from one year to the next. In some years, your default rate will be low. In some years, your default rate will be high. Okay, so if I were to take into account common factors which affect my N borrowers, I am essentially acknowledging that there is some amount of systematic risk involved in lending to these N borrowers. Okay, and the word systematic comes in when you have a common factor which affects all your borrowers. Okay, so you have some amount of systematic risk. You also have some amount of systemic risk. You can think of systemic risk to be one which comes from credit contagion. Okay, it might be the case that your N borrowers might be involved with each other in some form of a trading or let's say business relationship. If one borrower were to default, then its business partners will also feel the brunt of the default of that defaulted borrower, and there is a high tendency that the business partners of a defaulted borrower will also default. Okay, and that is what we refer to as systemic risk. So in reality, because we have systematic risk and systemic risk, this assumption of independent defaults is not defendable. Therefore, it can very well be the case that the X that you observe is very much different from the expected value of X. Okay, here we were saying that X is always very close to the expected value of X. Here we are saying that because of systematic risk and systemic risk, X can very well, diverge from the expected value of X. The risky scenario is one in which X that you observe is too high compared to the expected value of X. Okay, so let's do this. To prepare for a scenario in which X comes out to be very high, let's pick a confidence level. A confidence level at which you will be picking that high value of X. For regulatory capital purpose, please note that the confidence level which is stipulated by regulators is 99.9%. So let's do this. Let's pick X at 99.9% confidence based on the assumed distribution of X. Multiply it with 462 and you will get the worst case loss at 99.9% confidence. Okay, so since X is log normally distributed, to find the 99.9% value of X picked from the distribution of X, you will have to basically find out the 99.9% quantile picked from the standard normal distribution. Use the CDF tables for this purpose. Let that number be 3.0902. Multiply this number with 0.88, which is the standard deviation of the log of X, plus the mean of the log of X, and then exponentiate this entire number. And what you will get is the quantile of X picked corresponding to 99.9% confidence. Okay, so this is my worst case value of X, multiply it with 462 and I'll get my worst case value of the loss. Please punch in these numbers and confirm that the worst case value of the loss is 71.232 million. Okay, so on this distribution of my losses, I have marked both the expected loss and the worst case loss using these vertical pillars. Okay, now please note that since the expected loss is kind of predictable, is kind of part and parcel of a lending business, I am assuming that there is a provision account already set up for this purpose, an account which has been filled by charging this amount to your borrowers as part of interest rates, as a spread over interest rates. Okay, so this portion of the loss is already covered for using the provision account. We only need to have capital in place that can give us a buffer against this portion of this extreme loss. Okay, this portion is referred to as unexpected loss. It's the difference between a quantile loss picked at a certain level of confidence and the expected loss. So from a regulatory perspective, the equity capital required will be equal to 71.232 minus 6.915, and that is $64.317 million. Okay. Let's very quickly also work out the economic capital. Please note that economic capital is computed on the basis of a certain target probability of default, a probability number which bank ABC wants to target for itself. Let me assume that bank ABC has a certain target rating in mind, for example, a AA rating. Okay, bank ABC has already found this out from rating agencies that this rating will be granted to bank ABC if it can prove that it has enough balance sheet strength. Let's say it has enough capital in place for it to be able to withstand losses which have a probability of 0.03% of being exceeded. Okay, so if I were to have a loss number in mind whose probability of being exceeded is only 0.03%, and if I were to place capital such that I have enough buffers to withstand that kind of a loss, then I will be granted this rating of AA. Okay, so if this is my target probability of default, I can arrive at a confidence level to determine my extreme loss by flipping this number around. So confidence level will be 100% minus 0.03%, which is 99.97%. If I were to repeat the same calculations which I did for my regulatory capital by just replacing the confidence level from 99.9% to 99.97%, you can quickly convince yourself that the capital requirement, it comes to $89.28 million. This is your economic capital. Okay, this small example was for us to understand why banks need to have equity capital in place as a buffer against credit risk related losses, and also how to determine both regulatory capital as well as economic capital.